Okay. So, now let us see for the monotone valuations. Okay. So, definition is written there if you forgot the definition for the monotone valuations. Okay. Okay. So, this is the algorithm given in, by the way, the algorithm that we discussed, round robin algorithm, as far as I recall, it is written there, but I think that was 2018, EC 2018, okay, and this is in 2004. Okay. Obviously, monotone valuations, this algorithm will capture additive valuations as well, right? Additive valuations are monotone valuations. Okay. So, but what happens, there is a difference in the running time, and that is an exercise for you. Okay. To check, I just said polynomial time, but I did not tell you the precisely what is the running time. Okay. I hope you have done the tutorial sheet, solved the tutorial sheet that was shared with you. Okay. Okay. So, let us look at this algorithm now. So, what we do here is, let us say you have an allocation. Now, when I am saying allocation, it is not the final allocation, it is a partial allocation. Okay. So, to begin with, it could be empty. Nobody has anything. Okay. Now, we will create a graph, directed graph, we are just calling it NV graph, because the graph is there to capture the NV. Okay. Okay. So, what is the vertex set? It is a graph, I need to talk about the vertex set and edge set, right. So, what is the vertex set? Just the set of all agents. Now, if agent I envies agent j in A, then you add an arc from I to j. That is all is the construction. Is the construction of clear of the NV graph? NV graph is always defined with respect to an allocation, that need not be complete allocation. Whatever partial allocation I have, I will construct this graph, right. Vertex set of this graph is the all the agents. If an agent I envies agent j, then we have an arc from I to j. I will just, yeah. So, I will quickly repeat.
Thank you.
So, this algorithm is for general monotone valuation. Now, given an allocation, we will create an NV graph. Okay. And when we are saying allocation here, it need not be complete allocation, it is just a partial allocation, and to begin with it could be empty allocation. Okay. So, now vertex set of this graph is set of all agents, and now edge set is just a directed graph, we are calling it NV graph because it is to capture NV. Now, if an agent I envies agent j, then we add an arc I to j.
But this is undefined.
What is undefined? Okay. Now, what you will do, if there is an agent with integrity 0, okay, which is called as source vertex, from now onwards I will say source vertex. Okay. So, then if there is an agent, you will just assign any unallocated item to this person.
So, this could be a partial.
Yes. So, A is not a complete allocation, it could be partial, okay, and that is why I said to begin with it could be empty. Okay. Then there is no, I will just come to that. Okay. So, here there is nothing about giving any priority, choose, go, pick your min, maximum, nothing. Okay. There is a source agent, pick any source agent, pick any unallocated item to this person.
But one at a time.
One at a time. Okay. Okay. If there is, as long as there is a source vertex, do it. If there is no source vertex, then we will design a process to eliminate this cycle. Okay. Okay. Now, here this shorter one is actually not something.
No, I still don't know.
Otherwise, there is a cycle.
Correct.
Why there is a cycle? I just don't like why it cannot be that what you have is a tag.
But then there is a source vertex.
Okay, fine. Okay,
Yeah.
sorted.
So, if there is no source vertex, then it happens, right, and then we will eliminate, okay, and we will, this shorter one I am taking just because it simplifies the proof, okay. In the original algorithm they do not talk about shorter, you can take any cycle, okay, and we will do something. okay, and you eliminate this cycle, and we just repeat what happened. Repeat this process unless there, as long as there are.
Allocating any of the unallocated resource to the source.
Correct.
So it
We'll
could
look at
also become the maximum one that it likes as such. Or
it could be, but let's see. Let's run on this example. Okay. So initially nobody has anything, so allocation is empty. These are my vertices of the graph, agents. Okay. Nobody envies anyone, so there is no arc. Now I can pick anyone as source and assign anything to this person. Let's say I assign. Okay. Now let us see what is the graph now. Okay. Of course, Alice and David do not have anything; they will envy. So we have this arc. Okay. Okay. Do I have source vertex? Right. I can pick any one of them and I assign any unallocated item. Okay. Now let us again see what happens. Right. A vertex within degree 0. Okay. So now what happens with this arc? See, does Alice still envies Bob? So remove this arc. David will envy. Okay. Now Bob also envies Alice. David also envies. Okay. Do I have a source vertex? I still have a source vertex. Assign it. Okay. Again, let's look at what the graph may still change. Okay. Oh, okay. So we have, now there is no source vertex, right? We have this cycle. Okay. Now before doing reallocation and all, let us first understand what does this cycle mean. Okay. Then reallocation will be clear to you. One more thing, when we get in this particular example, you have cycle and everybody has just one item, right? But it is not a general case. When you get the cycle, it is possible that people have more than one item, that is possible. Okay. We are not denying of any of those things. Okay. Okay. So now, what does this arc mean?
each other wants the
Next one's item, next one's bundle, right? Everybody. So if you look at this arc, I don't know what is called head and what is tail, but if this is pointing to this, right, it means this agent likes her bundle more, and so on and so forth, right? That is why what we do, we reallocate items. Okay. So this person likes her bundle more, so let's give this to this guy. Okay. So now you see, cycle is in this direction, but reallocation will happen in opposite direction.
Can we say that this is like blocking cycle in some sense?
You can give whatever name you want to give, but yes, this cycle does capture and
You're
view.
moving subset.
No, full bundle.
That's it. Whole bundle.
Yes, yes, correct. So we move, we give this to this, this to this, this to this. Is the intuition clear?
Yes.
Why did we do that? Okay. Okay. So now if you do this, let's see what happens with the NV. We will argue what will happen with the edges. Okay. But I will argue that if you take the shorter one, everything will vanish. Okay. Shorter cycle. Okay. Now again, we have source vertex, right? So let's go and allocate. Okay. Now allocation is complete, at least for this, but this is the algorithm. Is the algorithm clear?
You could give donut to anyone.
You could give donut to anyone.
Is it like the rock trading cycle? Is it like rock trading cycle?
In some sense, yes.
Don't we draw any lines?
You can draw, but allocation is complete, so I don't care. Allocation is complete, right?
They can still envy, right?
They can still envy. I am not saying this is envy free allocation. I will argue this is EF1 allocation.
So you were saying that when allocation is done, there won't be any cycles.
I'm not saying that. When did I say that? When I reallocated, then those edges disappeared. I'm not drawing because I don't need to draw. The allocation is complete.
NV cycle is removed, but NV is there.
No, now when you allocate this, wait. Now when you allocate this thing, right? When I am always updating my graph, when I allocated an item to an agent, right? I just allocated an item, correct? Of course, graph will again change. Of course, you may have NVs, okay? But why do I care about that? Do I need to do any allocation? What was the purpose of constructing graph? If there is a source vertex, I will allocate some item, right? And if there is no source vertex, I wanted to eliminate NV so that eventually I get a source vertex. That was my idea.
So, if you at the end, suppose by mistake at this point of time, let's draw this NV graph or whatever. It turns out to be that. It means it does not have any directed cycle. Does it mean that this EF1 allocation is also EF allocation?
No, it is not, right? Because you have edges. Arc is to capture NV.
So she's not drawing it now because it is completely animated. But other is they both will still.
Is there any other question or is the algorithm clear?
Can I assign the donor to anyone and it will still be EF1?
We will argue that, but yes. Actually, that argument is very easy. We'll just come to that. But do you first understand the algorithm? Okay, let's first understand the algorithm. Okay, is that clear to everybody? What is the algorithm? Let's just recall once again. So we have some partial allocation with us, right? With respect to every agent, we have a vertex, right? Now, if an agent I envies agent J, I will add an arc. Okay? Okay. If there is a source vertex, now I am slightly moving towards the proof. Okay? If there is a source vertex, what does it mean? What is the meaning of source vertex? Nobody envies him. Okay? Nobody envies him, right? And I am allocating item to this person now. So, if I forget about this item, does anybody envies? That is exactly the proof of EF1. Now, you understand why am I allocating to source person? Because nobody envies him at this point of time, and now I am allocating to this person, right? So, if I forget this item, then nobody envies him. Okay? Okay. And if there is no such vertex, right, then I cannot apply the same argument because everybody envies everybody. Sorry, yeah, everybody envies someone at least. Everybody is envied by someone. That is also correct, right? Okay. So, then I am trying to eliminate this cycle. Why am I reallocating? Because I am trying to eliminate this cycle. Okay. Why am I able to eliminate the cycle? That needs a proof, right? When I eliminate this cycle, why am I getting eventually again a source vertex, right? That needs a proof, right? Because that is a termination criteria of my algorithm.
But in one round, you might be eliminating several cycles.
I don't care. Because all I care is there should be one source vertex for me whom I can allocate. Okay. So, suppose that the algorithm terminates. Okay. This we already argued. Is this clear? Why is it AF1? Because we always assign item to source agent whom nobody envies, right? So, if envy could be because of last allocated item only, forget it, you do not have envy. This is the main question here.
Like, okay, I still don't understand. Okay, for the source guy it is true, but why it is true?
But you always assign to source agent. The algorithm says you always assign to source agent.
Yeah, that's fine. You always assign to a source agent, but source agent at some point of time.
Initially everybody is source,
Correct.
right? So every step you always assign to a source vertex. If there is no source vertex, you first eliminate cycle, then we will argue that you will have a source vertex. Because we will argue that when you eliminate this cycle, this particular cycle, the number of edges in this NB graph will also decrease, right? So keep removing cycle as long as you do not find the source vertex. So there will be a time there you will again get a source vertex.
Yeah, but like look at the last stage, right? You have allocation of everything.
Okay.
Right? I need to argue that this allocation is EF1.
Correct.
Right? So I agree that for the source people, maybe it is current source, but there are other non-source vertices which also has some allocation.
Correct.
Like just because you did something in the previous steps,
Uh-huh.
when they were like, you were allocating something when they were source,
But you always assign to source,
but in some previous step.
right?
But
But
how
now,
do you know that? How do you know that he's like? How do you know that after some point of time, some other items are allocated?
because I always update the NB graph. I allocate an item and I update the NB graph,
Right.
right? Okay. Let's say I assign something to an agent now because he was source. Okay. Now NB graph updated. Okay. Whom will I assign? Again a source vertex only. So nobody NB'd him. That is by his source.
I think there is more arguments.
No, no, there is
When
no.
you give the item to the person, and at that time, was like that person was the source. So if there are some edges, then like we can observe that we can remove those edges by just removing one item, because that NB was created by adding only one item. After that, we are
So that is true about that guy's also.
Correct.
What about other people? So
yeah, because to remove that NB, we will be removing the item
from that particular object, not from the like. How do you argue about the vertex, which has like say 50 incoming edges and 100 outgoing edges? How do you argue about
Yeah.
that guy's? There should be some other way to do it, no?
So we argue this.
Huh?
You're asking if it preserves or not, the conditions preserve or not as we go on.
I mean,
So,
at least this is not evident to me. That
Let's understand this way.
On between two vertices.
At every iteration, it needs to be a EF1.
it needs to be.
It is EF1 at every iteration.
Okay, so that's it. Then you are arguing something very different. So then you are maintaining an invariant
Correct.
that at the end of everything,
Yes.
the current set of items are like if this is my universe, then
Correct.
that partition is EF1.
Right.
Right? So now, so hence my induction hypothesis is true about n minus 1 allocation, and hence now what happens if I do one allocation? Then that's a different.
Yeah, that's a like formal argument, complete argument. But in every iteration, why it happens? Because in every iteration, is that okay? So in I minus 1 iterations, let's say, okay, it is EF1, right?
Fine. Like I can formalize the proof.
Yeah.
But like, but it is absolutely not obvious that just because they have been doing this allocation to source, the last round, whatever allocation is, and all I'm saying it requires proof. It is.
Yeah.
It's not obvious.
Yeah, that's right. So formal argument requires induction, right? But okay, but that's the intuition that why is it getting in every iteration? Why is it a EF1? Because you are assigning to source, right? Because look at the other guys, okay? They are EF1 because of.
I'm not following the point, Pallavi. Is
Uh-huh.
that once you eliminate cycles, there are a lot of reallocations.
I will argue that.
No, so hence,
No, when you-
hence
correct.
whatever you started to happen, so you might have allotted to him in the beginning, right?
Correct.
When, but now when I do sort of cycle elimination, I take my things and just move around wherever. So the property that I allotted some bundle was made when some other vertex was sourced, might that change?
Agree,
But
agree.
once you did it, something happened and then everything just moved.
Right, we will argue that. Cycle level part we will argue ki what happens with the respect to the reallocations. Okay, what happens with the arcs. Okay, so let us see This was an my NV cycle, okay. And let us say this is the shortest one. Yes.
Can we change envy to hate?
What? What?
Envy graph to hate graph.
No.
Like
Sounds like some kind of
See, this is the notion. You need to live with it. Okay. So this is the NV cycle. Okay. Now, and let's say this is the allocation. Okay. Let us see. Now we reallocate. Okay. So A2 goes. This will happen, right? Now because it was shorter, I can say that what happened earlier. X5 likes A1 more than A5. It is not a right. It's bundle dependent. It's not a agent dependent, right? X5 likes A5 more than A1, but not others. Correct? Sorry, X5 likes A1 more than A5, right? But not others. Okay. But now X5 has A1, right? But X5 does not like. Okay, X5 does not like A2 over A5. Agree? Right, because we do not have arc. So similarly, now because A1 is more valued, X5 does not like this thing. Okay. So these all arcs will disappear. Agree? Now let us look at with respect to the arc.
Why is it not possible in the algorithm that I like my bundle more than your bundle, you like my bundle more than your bundle?
It can happen.
Then I get a two cycle.
Correct.
Then
You exchange on that.
That will be the shortest.
wait, then does it mean that now I like?
No, now it cannot happen because it was not equality.
And self loops are not there.
Self loop is not there, but he is talking about two cycles.
What statement are we making about the current utility and the new utility after exchange? Does it always increase? My current use.
See?
For all the edges, no?
Huh?
So,
For all these agents, it will increase, right? Because why do you have arc? You have arc because you like that bundle much. You like that bundle more than your own bundle. Correct? Now, you are getting that bundle. Right? So, of course, your utility is increasing. Okay? But that's not the point here. The point is that after eliminating NV cycle, do I have a source vertex? Okay? And what happens with respect to the NV of other people? Okay, that is the point here. Okay, does it happen that if I reallocate, NV of someone increases? That was Saket's point, right? That if I reallocate, then does the NV of some person increase? Okay. So,
So, am I correct that suppose some person has an incoming edge?
we are drawing that.
We just like place a small graph.
We are just drawing that. Just wait, hold for a minute. Okay. So this is what we argued with respect to the agents within a cycle. But there are people outside also, right? So let us say there was an agent P who liked.
With respect to X5, how are we comparing E1 and E2? In the original one, with respect
So,
to X5, we got
Correct.
E1 and E2.
First compare A5 and A2. You can write down also. First compare A5 and A2. We do not have arc. Correct?
It's not like we are not representing or we don't have.
We don't have. It's a short cycle. Is that okay? So let us look at an agent who is outside this cycle. Okay, and let us say that person liked A5. Okay. Now fine, A5 is still there. He will still this thing, right? This reallocation does not. It will not happen that it was not envying earlier and now he will start envying. Okay, just this agent change. That's it. Huh? Envy just, yes, the agent change because agent is with respect to this thing. Okay? Okay. Because whatever valuations are not, valuation change only for the vertices who are inside the cycle, not for the outside world, right? Their allocation is same. Okay? Okay. So for this it will happen. Now, it may also happen that arc was going from cycle to outside world. Okay. Let us say this was the case, right. Okay. So, now x2 is getting something better than previous cycle, right. So, what will happen? This might exist, might not exist, because now x2 get better bundle, right. So, it does not, oops. So, we know that number of edges do not increase with respect to this new allocation, it always decrease, right. Okay. So, I keep deleting, I know that I will eventually, because there are m edges only, I will get a source vertex again, okay, and then I can reallocate again. I can allocate to this person who is source, okay. Okay. Is the algorithm clear now? Any question? Okay. So, as I said that EF1 is a very strong, weak, I do not know what should it be called, such notion of NV freeness, right, that there was such a valuable item in the other bundle, right, I delete it and then I am saying okay, I do not NV. Okay. So, that is the shortcoming of EF1 that people think. Okay. So, your exercise question was to check the precise running time of both the algorithms and compare. Both are polynomial time, but what is the precisely the running time? Both the algorithms, round robin and NV cycle. Yeah. Okay. So, people defined another notion of NV freeness, that is up to any good. Okay. It means that no matter what item I remove, like remove items one by one, then also it should be NV free. For example, if I remove house, then also Alice should not NV Bob. If I remove coffee machine, then also Alice should not NV Bob. Okay. Up to any good. Earlier it was that there exists some good, if I remove that particular good, then it is NV free, right. Now we are saying no, it is not that, it should be true with respect to any good. For all and there exists, that is the difference. Okay. So, now this makes more sense to people, right. So, is this allocation satisfy this? But is there any other allocation that satisfies this? Huh?
We give 5 to this girl, Alice.
Correct. So, this notion is called EFX. Okay. So, just one thing, that x is not like a variable here, you think that EF1 and EFX. Okay, it is not like that. I mean, this was the confusion when I read these definitions for the first time. Okay. So, this allocation is not EFX. This was proposed in 2016, this fairness notion. Okay. So, as he said, if I look at this allocation, this is EFX. Why? Yeah, if you forget 1000, it was only one thing, Bob does not envy Alice, right. From Alice's perspective, if you forget car, then also she does not envy Bob.
Does not envy
Huh?
Bob anyhow.
Oh yeah, that's right. Alice does not envy anyhow. Anyway. Okay. Is the difference clear between EF1 and EFX? Yeah. EFX definition? Yeah. So, so the EFX definition is okay, I do not have mathematical definition, let me write it. VI AI valuation of agent I for her own bundle is greater than equal to VI bundle of agent J minus a good G that belongs to AJ for all G.
That is not for all. This one will be EFX.
EFX only I am saying. Okay. And in EF1 this was there exist. That is the only difference. Okay. EFX solution in general I will come to that, but it always exists. So, for general when I say I am talking about monotone only because that is the common assumption in fair allocation, general but identical valuations. Okay. Yes, general meaning it is not additive, right. So, it is a monotone, but identical meaning everybody values every item equally, those functions. So, identical meaning this is same, but this need not be additive, this is monotone. Okay. This is same for all agents, but it is monotone. Huh? So, identical meaning this for you like this. For every agent valuation for all the items is same, but this right, but monotone because this UI function itself could be monotone. For every bundle it is same with respect to agents. Okay. Okay. This exists, but we cannot compute it in polynomial time. Okay. That is known. Okay. So, this we know. I think cell weak. Okay. Now, when we talk about additive valuations, then for at most 3 agents it always exists. Okay. And for at least 4 agents it is open, we do not know. And for general valuation the same paper has for at most 2 agents and 3 agents we do not know. Okay. So, these are just some possible questions which are open, but if you want you can think because I will say in a minute why. Okay. So, we know that EF allocation need not exist even for the identical valuations, right. Checking is also NP hard, right, but what next that we can ask. When there is only one item type, what does that mean? Currently we were looking at it from the agent perspective. Okay. Now, let us write down these valuations from the item side. Okay. So, there are n agents. Okay. Let us say this is an item I1. Okay. Let us write this vector n sized vector. This is the valuation for the first agent, second agent, third agent, n agent. Okay. So, jth cell represent the I1 item का valuation for jth agent. Huh? Forget about use case for now. Okay. It's not about use case. We are just interpreting what do I mean by like I'm just defining a vector. It's just a defining. Okay. Okay. So, for now you looked at everything from the agent side, right. You define, okay, from agent side you listed I value item this one, right. So, from the agent side I had this vector. Now, I am saying let us look at from the item side. From item side now you have this vector. Okay. Okay. One item type meaning for every items this is same. Okay. So, this is fine, this one can do, this is something known, but when there are 2 item types we do not know. Okay. I am talking about EF only for now. Matlab there are 2 such vectors. 2 such vectors, meaning I can write this vector for I1, I2, Im, right, right, but there are only 2 distinct vectors. This is called vector, right? So, if I list down for all the items, there are only 2 distinct vectors. Do you understand the meaning? If this is 1, 2, 4, 2, wait, identical thing I did not define with respect to items. Will you call these vectors as identical or not? No, you are right, these are not identical. Okay. So, you list down these vectors, look at distinct vectors. How many distinct vectors you have? Just 2. Okay, that is it. Okay, we do not know even for this if the EF solution exists or not exist.
And in identical valuation, say that if
Identical valuation, when you say
when with respect to player's perspective,
that
then
is
this
does not
vector
exist.
will just have one number applicated. One.
Why?
Like each player has associated value of 5 with this object. Then here everywhere there will be 5.
You are saying that if it is identical, then I will have this.
Yes. Because each player.
Correct. Okay. So, this is something interesting, we can think about it, that even when the valuations are binary, okay, it is 0 and 1, that is it. Then also we do not know if EF solution exists or not exist. Okay. So, one can start thinking from, I never thought about it, but one can start thinking of, because NV free solution definition you understand now, right? Now, you can try to see how things happen. Okay. Any relation that you see between NV free EF1 and EFX? Wait. How many of you see some relation between EF, EF1 and EFX? So, here you just need to apply your definition, nothing else. If you did not understand the algorithms, it is fine. Wait now. This is a test to check if you understand the definitions. See, definitions are, I think, written also. At least some of the definitions are written. EF is there, EFX is here. If you replace this with there exists, EF1 is also here. Now, do you see now? Yes. Okay. Okay. When I say, do you see? Okay. Let's phrase this thing, that if an I want to ask that if an allocation is EF NV free, can I say something about EF1 EFX? Correct. Right. So, EF implies EFX, EFX imply EF1. I mean, just apply your definitions, right? If something is NV free, correct? I know NV valuation, my valuation is more than my valuation for your bundle, right? So, if I remove your good,
It will be even.
correct. See, I'm restricting myself to goods, because when we go to chores, there are similar notions, but definitions will slightly change, okay? So, just don't confuse with anything else. We are in good setting still, okay, and indivisible setting, okay. But if you can see that the converse was not true, okay. So, this is another notion. I think you were talking about envying to one person and envying to multiple person, right. So, this is what is captured in degree of envy. This is not studied much. Okay. But this paper is also mostly experimental kind of paper, which formalized this degree of NV notion. Okay. So, what is this? Again you define the NV between pair of agents. Okay. So, now we are moving towards the optimization question. Okay. So, we will quantify how much I NV, but how much. Okay. Okay. So, degree to which agent I NVs agent J under allocation A. Okay. So, again this can be defined in multiple ways. Positive, matlab there is nothing negative. Okay. If I like my bundle more than your bundle, right, I do not envy, and that is not also captured here, you are getting 0, right. But if I like your bundle more than my own bundle, then that value will come here. Okay. But there is also a notion of total NV. Okay. So, if we talk about total NV, then you can see that if I like my bundle much more than your bundle, then that value is also computed.
So for individual agent, will that be summation?
We will come to that. Currently, we are talking about pair wise. Okay. So, you see here this is again I would say comparatively you know more fair in the sense that I envy you, but with respect to some other person, if I am getting better bundle, then I am considering that as well, right. I am not neutral towards my happiness in some sense, right. So, this is what is captured in the total envy between a pair of agents. Okay. Boolean, that it is just 0 1, if I envy or I do not envy, that is it. Okay. So, this is envy between pair of agents, right. So, once I compute it, I can talk about envy of a single agent. Okay. So, now envy of agent I towards rest of the society, you just can take summation.
Can you once repeat the total?
Total is just a difference between this, right, difference between the utilities. So, the difference between first two is that if I like my bundle more than your bundle, right, then this will give you 0, correct, but this will give you negative, right. So, this is like considering everything, that if I like my bundle more than your bundle, it is negative, fine, but if I like her bundle more than my bundle, right, then that is positive, and that is, you know, it is okay.
Maybe we are seeing that like kind of being grateful. I have.
Yeah, exactly. Towards the society, we are trying to be grateful that okay, I envy some people to some extent, but I also get, I am better than some people at least. Okay, is that sense. Okay. So, difference matters here. So, if, for example, if between us I envy her 3 and I like my bundle 3 more than your bundle, then it is fine. Okay. So, I can take summation, okay, and I can also take max, my maximum envy towards something, towards this society. Okay. And then people study envy of society. Now, this is the final notion. Okay. So, again we can talk about summation, we can talk about maximization, and this we would like to minimize. Okay. Okay. So, most of these problems are hard, meaning cannot hope for polynomial time solvable problem. So, here the question is that you can take all possible combinations. Okay. So, now the NV cycle elimination that we discussed, okay, in the paper, that algorithm actually is for this positive, max, max. Okay, the same algorithm like the way it is written, it is for this max, max. Though this notion came later, but that works for this. Okay, this is what they try to minimize, same algorithm. Okay. Summing over the NVs of all the agents. So, it is in these layers. First you compute NV between every pair of agents, then you compute NV of a single agent using one of this criteria, right, and then you take the summation of NVs of all the agents. Okay. 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 So there is also one more thing, NV ratio. Okay. So in NV ratio, we instead of subtraction, we take ratio, and this is 1. Okay. 0 makes sense here, and in ratio 1 will make sense. Okay. Okay. So again I said that this is not much studied, but for NV ratio, people have studied some approximation algorithms. Okay. For this, because the optimal solution may have value 0, right. So that is why approximation is not there, but again they change the definition. There are some such things where you consider this as 1. Okay. Then there is something, some approximations are known, but that depends on the valuation functions. Okay.
Why 0 is the issue for the approximation?
Because this value could be 0, right. So alpha can be whatever. Okay. Okay. So this is just some history, and you know, if somebody wants to work on, so then these are the things. Okay. Okay. You seem so excited to see subsidy. Okay. So in auction lectures, we looked at price models. Okay. So NV free solution does not exist. Okay. Now, okay. Now this is like, can we give subsidy, right? Can we pay some price such that now NV free solution exists? Now what is the notion of NV freeness with respect to price? Okay. Okay. So now your solution is not just allocation, it will also have some price factor. Okay. And because it's subsidy model, you are not paying anything. You are always paid, or 0. So Pi is greater than equal to 0. Okay. And this is the notion of NV freeness. Okay. Values could be 0 as well. Now so this is something to note here, that utility you are deriving for your bundle, right, plus the price that you get, that should be greater than equal to utility you derive from the jth bundle plus price paid to jth person. Here you are not talking about your price.
This is like compensation.
Compensation, exactly, right. So is this definition clear? We will not talk much about subsidy model. Okay. Is the definition clear? Okay. Okay. Can we make any allocation NV free by this pricing model?
Do you mean exist a price vector for which this is this?
Can I come up with, like, I give you an allocation and I ask you, can you come up with a price vector so that it is NV free now? Okay.
So you give an allocation or can you change the allocation?
You are not allowed to change allocation.
This price factor is also fixed.
No, no, then there is no question. I am giving you allocation, right, and I am asking you, does there exist a price factor so that you make it NV free?
But I can take any price factor.
Let us see. You can take any price factor. That is a immediate answer, right, whenever we say this price.
By any amount.
Let us see. This will be of course the first thought, that okay, I can give any price, right, but the problem, there is a problem. Let us say this is my allocation. Okay, I have given ice cream to Alice but nothing to Bob. Okay, Bob envies Alice. Let us give 10 rupees to Bob. Is it NV free? Exactly. Now Bob envies Alice. no, sorry, now L is envies Bob.
Because it's P and P.
Exactly. Okay. Is it not moving? And actually we can check that, okay, now if you give 5 rupees to this, then Bob will start envying again.
Because people don't look at same object as same.
Exactly. Because I'll value
If you write some system of linear equations, if it has a solution, it can always this kind of thing.
yeah. So the point is that it is possible that you cannot make it envy free. Okay. But we are not saying that we cannot come up with an allocation that cannot be make envy free. Okay. Okay. So again, this is also a young field of research with subsidy, okay, in envy free literature, and with respect to other fairness notion, I am not even sure what is studied, but there is very less literature in this.
Identical valuations you can make.
I found this on the web.
For identical valuations, I can make this any allocation and make it.
Yeah, it's possible. Is it?
Because we get identical for, so I will just pay off whatever.
No, that's right. For identical you can do, right? I think you are right. For identical you can do, because you make, if this is 10, then you give 10 rupees to that person and it's fine, right? Maybe it's possible, you are right. Maybe, I mean, I think it is possible. Because whatever item is not assigned, you assign that much.
Just instead of item, I just give money.
Exactly, right. Okay. So now again, I will not go much into this, but what people study here, that can I come up with an allocation, right, and with I do not want to give too much subsidy. Okay. So there are results that, okay, if that much is the subsidy, you can come up with thing like n square, some such kind of bounds are there. Okay. But again, these are not much in this field. Okay. Okay, we are almost done with fairness notion. Okay, but if I have actually written it, okay, it's fine. So envy free, we saw two fairness notions. Okay, envy free and proportionality, right? And we saw that proportionality does not imply envy freeness, right? We had an example, okay, in which allocation was proportional but not envy free, right? What about opposite? What about opposite? Okay, just think for a while. Just apply the definition of envy freeness and proportionality. It is true. Okay, prove it in tutorial. It is just using the definition.
Because we know that all others are less valued.
Why
so
saying
it would
proof? Say the proof in tutorial. Okay. Okay. So envy freeness, this is a question mark, but it does imply. Okay. Okay. So there are several notions of fairness. Many more is also there. Okay. We will not talk about these fairness notion now. It is just to tell you that there is a lot. There is something called charity as well in envy free, that you donate some item and then what will happen. Okay. So such kind of things are there. Okay. So we talked about fairness so far. Okay. Let us talk about efficiency also now. Okay. Okay, just one question to you. Suppose I do not have the restriction of complete allocation. Okay. Now does envy free solution exist? Or some people are not allowed to speak. Suppose I do not have restriction of complete allocation. Okay. I said that I will have complete allocation, meaning I want to assign everything to someone. Okay. I restrict this, I relax this restriction. Okay. Now does envy free solution exist?
For any allocation.
No, now does envy free solution exist for any instance?
Yeah.
Some people were not allowed to speak. Okay, don't assign anything to anyone. Okay. Okay. So let's talk about now efficiency notion. This was for what? This was for NV free? Is it NV free? Okay, I have changed the valuations. Okay, is it NV free? No? Why? You are right, Alice NV is Bob.
Bob also
Is this EF1?
yes.
It is. Okay. Now at least everybody understands. I think everybody understands the EF1. It is EF1. Okay. Let us look at. Do you think this is the best we could do preserving EF1? Okay. Because now we are moving towards the efficiency. We are not relaxing our fairness criteria. We are still talking about fairness plus efficiency. Okay. Okay. So let us look at this allocation. Is it EF1? Is it better than previous one? For that you need to know previous one, but it was this 20 and 15. Okay. So is it better than? Now what do I mean by better? Better. If you recall, in the very beginning I talked about something, right? That someone is getting better, right? Without affecting the valuation of others. Pareto optimality. Okay. So what happened here? This is also EF1, but valuation of Bob and David improved. Right? Okay. So I am not saying that it is Pareto optimal. I have not checked that, but this is at least dominates the previous one. So this is the definition. Just to recall, this is the definition of Pareto optimality. An allocation is Pareto optimal if there is no other allocation A prime that gives as much utility as in A and is strictly better to at least one of the agent. Okay. I am left with actually 2 algorithms and then one PB lecture. Okay. This is the same example actually, that even the previous one was not Pareto optimal, because if you look at this one is better. Okay. Now you understand the definition, we do not need to really check this thing. Does EF1 and PO allocation always exist? EF1 always exist, fine. Now we are asking, does EF1 and PO always exist? Is the question clear? Who said yes? You have seen the algorithm. No, why do you think then?
I mean, if a set of solutions is EF1, one would be better in that.
Okay, let's see. It might be a cycle as well. Okay, but yes, you are right, it always exists. Okay. To show this existence, now we need to go to a different criteria, Nash welfare. This we did yesterday also, but let us recall what it is. Okay. Maximum Nash welfare, what is this definition? You want to maximize the geometric mean of agents' utilities. What does it mean? Okay. So, with respect to every allocation, I know the utility of every agent. That is still the same coming from my function. Okay. Now, you have utility for every agent, take the geometric mean, and that is what we want to maximize. We saw yesterday product, incorporative, okay fine, forget it, what we saw yesterday. This is the definition. Okay. We are talking about the Nash welfare, meaning geometric mean of agents' utilities, and that is what we want to maximize. Let us look at an example in case it is not clear. So, Nash welfare, utility of Bob is 20, Alice 15, David 15, right. Take the geometric mean, something will come. Okay. This is not the allocation that maximizes Nash welfare, and the goal here is not to tell you what is maximum Nash welfare. Okay. Just goal is just to tell you what is the definition. Okay. 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 So, if you recall, we are allowed to give 0 valuations, right. So, it may happen that Nash is 0, maximum Nash welfare is 0, then we may create some such examples, right. So, to avoid that, we will define this way. Okay. So, if there exists an allocation with positive Nash welfare, then output the one that maximizes the Nash welfare. Okay. Otherwise, first find a largest set of agents whom we can give the positive utilities. Okay. And out of that you want to find an allocation that maximizes Nash welfare of these agents. Okay. This they just redefined for this like in the fair allocation literature to avoid this 0 thing. Okay. Is the definition clear? Okay. Maximum Nash welfare again is not polynomial time computable problem, but we are not talking about the complexity for now, we are talking about the existence of EF1 and PO. Okay. And what is known that every maximum Nash welfare allocation is EF1 plus PO for additive valuations. Okay. So, let us prove this. Okay. Let us say A is an allocation that maximizes Nash welfare. There are 2 cases, it could be greater than 0, it could be equal to 0. Let us first consider it is greater than 0. Can I easily argue that it is Pareto optimal? Why?
If there was some other allocation, then that would have been maximizing the geometry, not this one.
Correct? If there is another allocation that dominates this one, right. So, everything remains same, one of them will improve, so product geometric mean will improve. So, that is simple, that it is Pareto optimal. Okay. Okay. Let us argue that A is also EF1. Okay. So, here we need to compute couple of things. So, suppose not, then there exists an agent I such that this will happen, correct? Okay. Let us see, where is this?
It is for all J.
Yeah, right, right. Okay. So, this thing I just need to argue one of the inequality, the choice of this G star. Okay. So, G star is just an item, right. You take the ratio okay. So, you G star is an item, you compute this ratio with respect to every good in AJ, right, which are positively valued. right. So, first thing we need to say that why it will happen that there are goods that are positively valued in the bundle of J, J's bundle. No. So, why this should happen? Why there is at least one good, right, which is valued positively? See, I am talking, yeah. My question is very simple. Why there are goods in the bundle of J, right, that are positively, why there is at least one good that is positively valued by I? Yes. You wait this way to answer. So, the argument is that the first thing is that because it is greater than 0, then at least for his own bundle its valuation is 0, greater than 0, right, because it is a product, right. Now, we are saying that I envies J, right. So, total valuation is more, right. So, at least there is one item for which you value greater than 0. Is it okay? Okay. So, G star is, you will understand why such a choice in a minute. That is just for mathematical calculation. Okay. Now, A prime is, let us say, an allocation that is obtained by moving G star from agent J to agent I. Okay. We are not doing anything, we are just analyzing. Okay. Now, we want to claim that Nash welfare of A prime is greater than Nash welfare of A.
G star from agent J to agent I meaning?
G star was an item with the J.
G star is an item in J.
Yeah.
G is an item.
Yeah, but G star is the one that gives you minimum ratio, right. So, G star is an item with J currently. Now, we are saying let us give it to I. Okay. This is reallocation. Okay. And now, the claim is that the Nash welfare of new allocation is more than the previous allocation, which will contradict that A was.
So there is something that J values less and I values more, and then because we are
let's
taking
see.
minimum of that, so maybe like I values it
Let us
higher.
see, it needs a bit of mathematical calculation, let us see, okay. It is not that immediate, okay. But you are right, that is the reason to pick this minimum, okay. Okay. So, we want to claim this. Let us see if I have more slides, otherwise we will use board. Okay. So, I have couple of more slides. So, basically I want to claim that Nash welfare of A prime divided by Nash welfare of A is greater than 1, right. So, product wise also I can say that it is greater than 1, right, otherwise after taking cube root how it. So, let us focus just on the product, right. Okay. Now, the allocate, let us just, you can write everything, other terms are just cancel out, let us say, let us see. So, you write the Nash welfare of A prime, you write the, like, forget about the roots, that does not matter, product, right, let us write, okay, we can write product here, okay. Okay. Notice that I only changed the allocation of I and J, correct. For everybody else it remains same. So, values will cancel out, okay. The only thing that will remain is the valuation of agent I with respect to new bundle and valuation of J with respect to new and old both, numerator and denominator, okay. Now, what are the valuations? With respect to new allocation, it is AI plus VI G star, okay, and for this minus VJ G star. These are the values. Look, I am using additivity here. then only I am able to write it.
How are you adding valuation to allocation?
One bracket is missing, bracket is just misplaced. I mean there should be a bracket here and there should be one bracket here also, that is it. Do you agree with this? So, now we wanted to show that this is greater than equal to 1, which is equivalent to showing that this is greater than equal to 1, right. Now, this we can write as 1 plus Vig star this thing, right. So, what is our, do not worry I will do it. So, our claim is now 1 plus Vig star divided by Vi Ai 1 minus, okay I can see here also, Vj G star we want to show that this is greater than 1, correct. Now you need to look at the board, okay. So, we want to show that this is greater than 1, right. We solve it, 1 minus Vj G star divided by I am just multiplying, nothing else. This is greater than 1, okay. What I want to show now, this quantity Vi is greater than Vj, it is strict, right, it is strict, Vj G star divided by Vj Aj plus Vi G star Vj G star again we are just under key what we want to show equivalently, okay. Then just two of our assumptions will lead us to these inequalities. Is greater than, no, this is it. So, this is what we want to show. Now, you can see that Vj G star is there also, Vj Aj is there also. So, I can take this common 1 plus this and this, correct. Okay. Now, Vi Ai is here, Vi Ai here also. So, I can say that Vj G star Vi G star is greater than Vj G star Vj Aj Vi Ai plus Vi G star. This is what I want to show, correct. All these things are equivalent, right. Once I show that, I can we know that Nash product of A prime is greater than Nash product of A. Okay. So, because this is our to show, let us forget about this thing. Yeah, black and blue is also there. Okay. So, now because of G star, what is the property of G star? Yeah, it is a minimum that gives me the it's an item that give me that minimum ratio, right. Okay. So, let us look at, see, okay, let us move this one also here, that will be useful for us. Okay. Let us bring Vig star here. And what was there? AI? VIAI? I do not think so, is it? I think it was J. It was J? What was it? It was not G star. G star is I moved here. VJAJ, you are right. It was VJAJ. Okay, this was it. Okay, now we know that G star is the one that minimizes this ratio, right. So, if I look at V J G star divided by V I G star. Okay. Now, what I am going to write, maybe that is some standard inequality, okay. But if you work it out, I actually worked it out and it is true, but maybe there is some standard inequality also that is possible. Okay. So, if you take this summation over everything, okay, G belongs to AJ. This is true, okay, and it happened because of the choice of the G star that it minimizes the ratio, okay. Then that is why this summation thing also we have, okay. So, you can just work it out and we can again talk about, if you are not able, I do not know if it is you know, some obvious known inequality, I do not know, but if you write down all this thing, then it works definitely, this I checked. Okay. Sakit maybe can say if this is some obvious inequality. But if we write, do some multiplication, do this is comparison, it works. Okay.
Like this is.
No, this is not component.
But this is inside that summation.
What is?
No. Okay.
Yeah. What is inside? Yes.
No, nothing. I got it.
Okay. So you just work it out. If you are not, then tutorial. During lunch hours, you just work it out. It works. Okay. So what is this? This is valuation of J for the bundle AJ, and what is this? This is valuation of I for bundle AJ. Okay. 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 I envies J, right. Now, because I envies J even after removing G star, okay. What does it mean? Why am I saying that it envies even after removing ZG star? Because it was not AF1, correct? Okay. So, now because of that, what do I have? Vi of AI plus Vi of G star, right. This is less than Vi AJ, correct? Is this fine? In case there is a confusion, because of AF1 definition, I can write that. Okay, is there a confusion by the way? because of EF1 definition, even if you remove G star, then also the valuation is less, correct. So, that is why I have this. Now, if you just multiply these inequalities, you will get this, that is it. Okay. Just multiply, it is this is the same thing. Okay. So, what do we know now? If Nash welfare was greater than 0, right, then there is an item, if I reallocate that, Nash welfare increases. Okay. Now, let us see what happens if Nash welfare was originally 0. Okay. So, when Nash welfare is 0, our definition was that we will first look at the set of agents that can get positive valuation, and out of that we want to maximize, correct. So, let us say S is the set of players to which the solution gives positive utility. Okay. Of course, S is the largest set by the definition. Okay. So, is it Pareto optimal? Due to the same reason, it is, correct. Okay. Okay. Now, let us argue that A is also EF1. Okay. First, let us see if I just talk about the agents within S, right, within S. Now, I can use the same argument that we just did to say that there is no NV between the agents in S, right, because if there is, let us consider that pair, do reallocation, and we can show that Nash welfare improves. Okay. So, using the same argument, we know that there is no NV between the pair of agents in S, within S. Outside it may be for now. Okay. Now, what is remaining to argue? That S does not, and agents in S do not envy agents in A minus S, right, and agents in A minus S do not envy agents in S. Okay. Now, agents in A minus S anyway getting 0 utility, right. So, agents in S, can they envy? No. So, they do not envy. Sorry. Okay. Now, what about agents in A minus S? We are not saying they do not envy, we will just argue that they do not envy up to 1 good. Okay. But for S to A minus S, they do not even envy. Okay. Okay. So, now this is what we want to argue, that agents in A minus S do not envy agents in S. Okay. Suppose not. Okay. Then there exists an agent I in A minus S that envies agent J up to 1 good, right. It means that, what does it mean? There is an item G in AJ, right, which is positively valued by J. J is in S. So, such an item exists. Agree? Okay. So, now look at this. If you remove Vi from, if you look at from the I's perspective, right, because it is not EF1. What does it mean? If you even remove G from J's bundle, then if you look at the utility from I's perspective, that is also greater than VIAI, because I envies up to 1 good. Do you agree or not? Everybody is silent now. If this does not happen, then it is EF1 up to EF1, right? If this does not happen, then it is EF1, right? So, now because it is not EF1, what do I know? Even if I remove 1 good, then also I envy, right? Forget about EFX for now. Even if I remove 1 good, then also I envy, correct? So, because you envy, right, and this valuation you know it was 0, so I know that this is greater than 0. That is all I need, that it is, this is greater than 0. Okay. Okay. So, what does it mean? there is one more good in ai minus g that is positively valued by I. Correct? Otherwise, how is valuation greater than 0? Okay. So, this happens. Now, let us give g prime to agent I, okay, from agent j to, yeah, let us give this item g prime to the agent I. Do you see any contradiction? Just wait a minute, for a minute. No, we cannot say Nash improves here, but we can say something else.
So S was already
Largest. Now, what happened? That I also has positive utility, correct? Does J also has positive utility now, right? Because G was the good which was positively valued by J and it is still with J, right? So, now we know that the number of items who could get positive utility increases. That is a contradiction here. Okay. We cannot argue that thing because maybe Nash welfare of J slightly decreases and all those things. Okay. Because same arguments we cannot apply. We use the fact there that denominator is greater than 0.
But now the allocation has changed.
Correct.
So S will change because S was defined for this allocation and the set of players to which this solution means allocation, right?
Correct.
So the set of players.
But S is also largest size of, if I look at size wise, right, then S is also largest such set by the definition of Nash welfare, right. But now what are we saying? Everybody who was getting positive utility in earlier is still getting the positive utility, but I is also getting the positive utility now, right. So, that contradicts that size of S was largest earlier. Okay. Any questions? Okay. So, okay. So, we just argued the existence, okay. But Nash welfare is NP-hard problem, that is not polytime, okay. But we do not know if computing AF1 plus PI allocation is NP-hard, okay. Complexity question is still open here. I will just stop after this. So, AF1 plus PO allocation we talked about additive valuations and you know that in the proof we used that it was additive, right. But it may not exist for sub-additive and super modular functions, but for sub-modular it is open, we do not know, okay. This is again a tutorial question, okay. I will explain what does it mean and you need to come up with an example, okay. So, it means that maybe your instance had a very simple AF solution, it exists, you could compute it, very simple example, right. But even if you find the maximum Nash welfare, right, the allocation that maximizes that, skip this solution. So, what are we trying to say here? That maximum Nash welfare allocation does not imply AF, it implies AF1 plus PO, but it does not imply AF, and you need to come up with an example for this. It is not just with 2-3 agents, 2 agents and few items you can come up with this thing, that is why I am leaving it tutorial, okay. Okay. So, let us stop here and then we will continue.